It's 180-degree field view. Stereoscopic, wide angle. So, so those on the CERN trip, I was taking some pictures in 3D, but you do need a 3D phone to be able to look at it. I can show you some if you're interested. But I'm going to try filming the lessons. I thought it'd be a bit more interesting if they were in 3 dimensions. So you could then get a little headset on and then, whoa, look, I'm in the room. There's me. I follow them around in the room. Yeah, as opposed to just a standard 2D lame sort of lesson. Anyway, my lessons will be 3-dimensional. So I just want to try it out basically, but you can be reassured it's 180-degree field view, so anyone behind there isn't going to get filmed. So all the frantic words and work and energy you're expending won't be captured. I don't know. I haven't actually played it back with the video yet. I've only been taking snapshots with it. So we got the two condition for SHM. Anyone want to give me one?
Accelerates.
Sorry?
It accelerates towards the equilibrium position.
It accelerates towards the equilibrium. Everyone happy with that? No? Who said that? Quite a few. So what should it be then? If it's not, it accelerates towards equilibrium. Well, come on, if it's not right, then you need to say what it is instead. You can't just say, oh, it's not right. You don't know what the answer is.
What do you mean by it?
I know it's not. I wouldn't say that's a condition. I would just say that's quality.
Okay, so what would you have said as well instead then?
I don't know.
What do you? Is it the way in which Will said it, or is it the content of what he said? Sorry?
I think the way you said it.
The way that it's been said.
Yeah.
Okay. Yes, you could probably say it without the it in, because I don't like it.
The object.
The object. Well, I'm more general than that even.
Well, we don't know what it is.
Well, the condition that has to be met for anything that's undergoing SHM is that the acceleration is always towards equilibrium. Yeah? So you're right, to be honest, the most important thing is you recognise that's a condition, really. Okay, now I'm just writing it down a little bit more in physics speak. The more important thing is you remember what it was. Yeah, because I didn't see a whole lot of other people desperately writing forward ideas, to be fair. So the acceleration is always towards equilibrium. Yeah? There is another way of saying that as well. There's 2 ways of saying the same thing with that one. This is going to be a very bad video, honestly. The other condition, remember what the... Okay, so...
Stop at the top and the bottom.
Well, to be honest, it's a little bit more subtle than that. So if this is the object on a mass on a spring, and it's going up between there and there, if I was to draw an arrow to show the... Now, why do you do this? Can you draw an arrow on there, on here, this diagram, to show me the displacement, and an arrow to show the acceleration in this position here, and it's at its highest amplitude. Ah, well. Sorry, mate. Better late than never. I would normally, the answer's correct. I would normally have the arrows starting at the point where the action is. Yeah, like we do forces, the arrow always starts at the point where it has it. But you've answered the question I asked you really in terms of what I was looking for, but just how you draw those things. That's better. Yeah.
How do you do that?
Well, where is the displacement 0? And start the arrow from where the displacement. You're right before that. You're right before where's the displacement 0? There. Yeah, and then have it going, and again, if I'm being there, because that's where that point there. No, look. No way around that. Right, come on. Displacement and acceleration of that mass when it's at the very top. Well, hey, not bad, not bad. So, the acceleration, this is the equilibrium point here. We just said acceleration is also the equilibrium. So, the acceleration will be that way. The displacement, though, you take the displacement from the equilibrium position, and where would that mass be in equilibrium? It would be in equilibrium there, and the displacement of this object from that point is, I'm doing it properly, up to there. So that would be the displacement, or as we use in SHM to show displacement x. Yeah. Everyone happy with that one? Yeah. What's happening? I mean, this is going to the stuff we did in little groups now. So the spring is sort of here now. What's happened to the size of acceleration? Is the acceleration getting bigger or smaller as the mass moves towards this equilibrium point here? So all I'm looking for is a bigger or smaller. Is the acceleration getting bigger or smaller as the mass goes down towards this equilibrium point? What's happening to the acceleration? Is it getting bigger or smaller? Or staying the same? I mean, to be fair, I should have included that as an option, or staying the same. Okay. Yeah, good. Hey, look, almost everyone's getting it right. I don't think you hear me. It's actually getting smaller. I mean, Jack, how do you know it's getting smaller?
Because that equilibrium is traveling faster. So,
and therefore, because that could just be staying the same, couldn't it?
Well, yeah, but as it goes past the equilibrium position, it's slowing down. So the
Deceleration.
acceleration in the opposite direction will be slowing down.
Yeah. Okay, that's fine. Meg, got another answer?
Another one of the conditions is that.
Oh, don't spoil it.
Okay.
Okay, that's fine. We'll come back to that one. We'll come back to that one in a second. Yeah, I want everyone to try and recall it rather than just you tell them what it is. I don't want you to steal my my next questions. So yeah, great shout, Jack. It once it goes past this equilibrium point, the mass starts decelerating. And actually, there's two possibilities. The acceleration could be constant, and then flip. It's really unusual in physics. And in fact, at the equilibrium point, if you recall, if we haven't pulled it down, if we just put a mass on a spring and stretched it to the equilibrium, it wouldn't be moving. And in fact, the forces on this object would be balanced. There's no resultant force on it. So we've got tension in that direction and we've got weight in this direction. Those two forces are the same. There's no resultant force on those two, no resultant force on that object. So if there's no resultant force, then the acceleration is also 0. So there's no acceleration at this point here. Okay, so the acceleration is getting smaller and smaller and smaller. Put on there. So that would be the displacement, and this would be the acceleration. And then when it just goes past the equilibrium point, so it's here now, then the displacement is going to be in this direction. And you said, Jack, it's decelerating. So what does that will mean about the direction of the acceleration? Which direction is it moving in? It's going, it's moving down. Is it speeding up or slowing down? Slowing down. So if it's slowing down, what direction must the acceleration be in? must be up in the opposite direction. Yeah. So acceleration actually is like that. And I'll carry on at the expense of rolling out my answer. So then it goes down to the bottom like that, and got acceleration like this, and displacement like that, and then it starts going back up again, like that, and the acceleration is like that, and the displacement is like that. Okay. So what can you see about the directions of displacement and acceleration? If you're saying, well, how is acceleration related to displacement at every point? They're in the opposite direction. So the other way of saying acceleration is always towards equilibrium, as it is, look, you can see it's all accelerating towards equilibrium, accelerating towards equilibrium. The other way of saying that is acceleration is always in the opposite direction to displacement. Now that's important because when we come to look at the graphs that show how this is oscillating back and forth, that I'll do tomorrow, Wednesday, then it's important you recognize that the displacement is always in the opposite direction to acceleration. Okay, so either one of those two statements, acceleration always towards equilibrium, or acceleration is the opposite direction to displacement, are both fine. First condition. Okay. Right. Second condition. Look, just to help you remind, a vector has magnitude and direction. And the two statements for SHM relate to the magnitude of acceleration and the direction of acceleration. So what we've just covered now is the direction, always towards equilibrium acceleration, or accelerations in the opposite direction to the displacement. The other condition is relating to the magnitude of acceleration. And next.
I thought it was that it's proportional to the
Is proportional
to the
minus displacement. What do you think about that then? Thank you for that. Correct? It's almost correct. And what's happened is, it's the minus bit, because actually if I come to the equation that relates these things, that the direction A is in opposite direction to displacement, and A is directly proportional to displacement, we can summarize mathematically, and we come up with, well, if something's directly proportional, then A equals some constant times X. Yeah, that's the equation if those two things are directly proportional to each other. In fact, the constant of proportionality, as you would have done on Friday, is actually, do you know what the constant of proportionality is? Tom?
Isn't it omega or something?
It is omega or something.
Oh, yeah.
Lowercase omega.
It's omega squared. And remember, omega is the Greek curly W. So it's just curly. Now you'll remember that, won't you? Because we did this in circular motion. So you'll be able to tell me what actually this is. Yeah, angular speed. Now that's what we call it. But what is it equal to? Sorry, Jack?
2 pi r over t.
Well, that's the special case. It's 2 pi over t, not 2 pi r. V actually, V is 2 pi r over t. And again, that's the equation. But if I said what is linear speed, how do we define it? We wouldn't define it as 2 pi r over t. We would define it as speed is distance travelled over time taken. meters per second. Yeah, of which that's a special case for something going in a circle where that's the radius and the circumference, the distance it's travelled is 2 pi r, and t is the time period, time for oscillation. So the time it takes to go around that. So basically it's how fast it's going when it's travelling in a circle. This one here, okay, I've got the equation, but what's the thing that goes in there? What's the equivalent? Jaden, there! That's just for the video, by the way, Jaden. Yeah.
Angle travel over the time.
Yeah, it's angle turn through. Angle turn through over the time taken, and again this is a special case for one complete rotation. That's the angle turn through, call it theta. In this particular case, one complete rotation is in radian, 2 pi radian. And the units of angular speed, if you remember, are radian per second. It's not degrees per second, it's actually radian per second. So that's all it is. It's an equivalent sort of thing to speed, like how fast is it going, but it's how quickly is it turning. And if you remember, this has got some advantages when we're looking at objects moving in circles. Can you remember what the advantage of using that thing is? If you had two objects on a rotating disc, A and B, sat on the disc spinning around, then B would be travelling faster than A because it has to go through a larger radius in the same time. So B travels faster than A travels more slowly, but A and B have the same angular speed. It doesn't depend on the radius. It takes the same time to turn through the same angle, and that makes life a lot easier in some situations. Okay, so that's what it is. I'm not going to explain why it's there, although there is an opportunity to do that later when we look at the equations representing mass on springs. So I may well show you, but you do not need to derive this to know where it comes from. Okay. Okay, so that's all it is. It's a measure of how fast it's spinning, and what I will show you, I think Graham went through this on Friday. For an object that's spinning round, that relates to an object moving up and down. Yeah. So there's a relationship between objects going in circles and objects going up and down, and that's why that's there. Yeah, because the speed at which it's turning around here affects the time that it takes to go up and down here. So a higher angular speed means it's turning through more angle in the same time, so that would be spinning faster, which would mean that this would be oscillating at a higher rate. So that tells you how quickly the thing's oscillating up and down. Okay. Well, that covers off the proportional bit, but how do we get this into it? The fact that A is in the opposite direction to X. That's where the minus sign comes in, because in vector terms, if something is moving along a line as these things are, if they're going up and down, then normally the normal convention is that that way would be positive and this way would be negative if everything's happening along the same line. And so because that's in the opposite direction to that one, I can just slip in a cheeky minus sign, and that shows me that they're in the opposite direction. So that's where the minus sign comes in. But I wouldn't necessarily need to say it's in a negative direction, just it's in the opposite direction. Okay, everyone happy with that then? I'll take that as a yes then. So that is the condition for SHM. Now what you will definitely get asked, and I don't think we haven't got that through, is sketching a graph of acceleration against displacement. Did we do that? Did I do that with some students or no? Have you got those two conditions written down on a piece of paper? Okay, good. Can you sketch a graph of acceleration against displacement for me, please? So there is the acceleration graph. This is the displacement graph. And let's suppose the amplitude of this oscillation is between A and minus A. You know, we use A for the amplitude of an oscillation. So again, coming back to my little mass on a spring example. So that's the equilibrium position. I've pulled it down to here, let's say. That would be minus A. Let it go, and then it goes up, and then that would be, see. And I want the limits on as well, please. Limits A. graph should look like this though, Jack. Yeah. It should be set in the middle. This is a classic case of me putting something in a context that if I put it in a different form for you, you'd all get it straight away. It looks different because I've got different letters here, but actually you've come across this sort of stuff before in maths. Yeah. I've got to say, it's not bad actually. Not bad. The number of people getting this is really impressive. So effectively, what we've got, this is the y-axis, that's the x-axis. I've got a on the y-axis. That's like saying a equals some minus some constant times x. Well, if I said, sketch me a graph of that, what would it look like? Well, y equals mx, straight line, negative gradient, like that. Yeah. The limits though, minus a and plus a, so that's to do with the displacement, plus a, minus a. Okay, so if I was to draw a graph where the spring was stiffer between the same limits, what do you think it would look like? Stiffer spring. Yeah, on the same one, and then can you label one? Well, which was S for stiffer. Just label one as S. Okay. Well, it's funny. I mean, almost everyone's gone for this as ever.
Is it just short?
Is it shorter?
The amplitude would be
We'll think about it. So, I mean, Jade, what are you going to say?
the amplitude would be a bit less.
Yeah. The amplitude would be a bit less. No, I've pulled it down to the same place. The amplitude's the same. Yeah. The amplitude has to be the same.
The acceleration would just be bigger, doesn't it?
The
acceleration would just be bigger.
Bigger. So what will that mean?
But it would be steeper for that.
Steeper graph. Tom, you got a. Okay. Will, you've got it being steeper. Why would it be there? It wouldn't displace as much. I've displaced it the same.
Higher tension.
And that's the important thing. So I've pulled it down and let it go from exactly the same place as I did before. Yeah, so the displacement is steeper. Why is it steeper? It's steeper, yeah? If that gives you any confidence, Will, it's the right answer. Well, it's got the higher acceleration. Obviously, now I've told you it's the right answer, the acceleration. But why is the acceleration going to be? Is there any way you can explain why the acceleration is higher? Will? Go on, yeah. Yeah. I'm having to apply a larger force to pull it down. That's why it's stiffer. So if the resultant force on that thing is bigger, then the acceleration must be bigger. How does that relate to how fast it's going to oscillate? It's got a steeper gradient, which actually represents this thing here, the angular speed. If it's stiffer, it's going to oscillate at a higher frequency, which means that this has to be bigger, which means the gradient has to be steeper. There's two ways of thinking about it. Just thinking about the forces and the accelerations, fine, or thinking about the frequency that it's oscillating at and making that becomes bigger. Because on the formula sheet, we came up with omega is 2 pi f. That's the frequency, and so if the frequency is higher, then the angular speed is higher, and therefore this is steeper. Have you got a copy of this graph in your notes then?
Yeah, I did it with Graham.
You did it with Graham?
Yeah.
So that's why everyone knows exactly what it looks like. Yeah? Okay, good. Right, well let's stop there. And I want to go through this practical stuff. I have your practical folder. So what I'm going to do, I'm going to hand this out and ask you to put your plan in it. And also if you have your graph from the mass on the spring investigation, you can also include that as well. And I'll also mark these, although I still need to mark another couple. So you'll see what's missing. And although some of you are bringing some stuff in as well, won't you, to put into it. You will have these in tomorrow. So if there's stuff outstanding, then I suggest you bring it in tomorrow. I haven't, what I've realised, I've not marked yours, annoyingly.
Can you send me the
What?
Sort it out.
Has everyone got theirs?
Yeah. He hasn't marked, and all for once I haven't done anything wrong.
So I haven't marked yours, Jane. So I don't know what's missing and what's not.
Oh,
Yeah. But I'll tell you, I'll take it home and I'll mark it tonight, okay? So you'll have it tomorrow. Is anyone else has not been marked? There were 3 I haven't marked, I think. Okay. So if you put your plan in there for the pendulum, because what I said was I'd mark it today. So right, let's stop that.